Hi everyone, welcome to our very first Facebook Live interview. I'm David Hosansky. I work in communications at the National Center for Atmospheric Research. And with me is Dr. Morris Weisman. He's a senior scientist and a brave soul who's decided to be our inaugural interview. Thank you, Morris. And Morris is an expert in thunderstorms and tornadoes. And let's start by, let me ask you how you got interested in these storms. You grew up on the East Coast, right?
I grew up in Rhode Island, and weather was something I was fascinated in from very, very young age. Watching the hurricanes come up the coast and the clouds and the winds and the thunderstorms coming in the summer, and I just couldn't not watch them. While I was in school, I got into trouble for looking out the window at the time.
A lot of us did that.
Yes, exactly. And running home at lunch to watch Don Ken on the TV to see what the weather was going to be for the rest of the day. And so I guess I'm what you consider a classic weather weenie from a very, very early age.
I see. And there were a number of weather weenies here at NCAR.
Oh, yes.
But you're tornado and thunderstorm weather in particular. That's what your research focuses on.
That's right. I came here in 1979 to work with one of the first numerical models, computer models of thunderstorms. And I had the privilege of pretty much being one of the first people to actually play with such a computer model that animates, that simulates what the winds and the precipitation do in these storms, and try to figure out, why storms act differently on different days.
Okay, and I think you've got an animation or two that could show how these storms develop. Is that right?
Yeah. What we've learned is that there are two different types of basic types of storms from the dynamic perspective. What we normally think of as a thunderstorm is an ordinary thunderstorm. And we have an animation that will be coming up and will be starting that just sort of shows a cloud that develops in an environment with no wind variation with height. Just an ordinary summertime thunderstorm. And it will animate from the beginning, and we'll see how the storm develops. You get a very strong updraft. Those updrafts sometimes can get as strong as 50 meters per second, which can produce huge amounts of rain. Then as the storm evolves, the rain falls from the cloud. We can repeat that again. And you'll see the storm develops, rain and sometimes hail develops, falls from the cloud, falls to the ground, evaporates, and you get this cold pool that develops at the surface. That's that cold gust of wind that you get when the thunderstorm and the rain and the hail come. This is what we refer to as an ordinary thunderstorm. Basically, the air is buoyant, just like bubbling in a boiling pot of water, and it accelerates upward when there's cold air aloft and relatively warm and humidity near the surface. This kind of thunderstorm can produce severe weather, large hail, flash flooding, all those kinds of things, but often does not produce the big tornadoes. It can produce some small tornadoes, but what we've learned over the years is that the storms that develop the really big tornadoes are a very different kind of thunderstorm. There's something we refer to as a supercell thunderstorm. And now we're going to look at an animation of a supercell thunderstorm. Don't start yet. And you'll see on the left is a profile of the winds. And the thing you'll notice that the winds are varying with height quite a bit, and coming in from the east, then going to the south, then to the west aloft. And that variation of wind with height does something very, very strange to an ordinary thunderstorm. It develops rotation in the storm. And as the storm animates, you'll see that this rotation that you can sort of see in the wind shear gets tilted up into the vertical. And what we see is the development of a low pressure center in the storm, which then can suck the air up. It's a rotating storm now with strong updraft and rotation together. So unlike an ordinary thunderstorm, a supercell thunderstorm is a rotating storm. And it's within these kinds of storms that we really get concerned about the possibility of the big tornadoes, large hail, and the highest winds.
And what would cause a supercell to form as opposed to an ordinary? Like, can you tell ahead of time?
Yeah. Yeah, there are two ingredients we look for. First is the instability in the atmosphere, the thermodynamic instability. And that's the relationship between the temperature aloft and the temperature and moisture at the surface. And the colder it is aloft relative to the warmer and more moist at the surface, the more unstable the air mass is. That's true for all thunderstorms, ordinary thunderstorms and supercell thunderstorms. But the ingredient that really makes supercell thunderstorms different is this variation of winds with height. And so you have like low-level winds from the east turning around to southerly at mid-levels to westerly, or southerly winds at the surface turning around to westerly winds at higher levels. So environments where the jet stream is overhead and the winds are varying very strongly with height, and there's thermodynamic instability, are the environments we look for supercell thunderstorms.
I see. Okay. How good are we at forecasting supercells and tornadoes?
Over the last 30, 40 years, we've gotten very, very good at forecasting supercell storms. We can see the large-scale environment, and sometimes 3, 4, 5 days in advance, computer models will see the ingredients come together. And the Weather Service people will see that those hints, and they'll actually put out severe thunderstorm watches well in advance, sometimes days in advance, warning people that this environment's going to be conducive to thunderstorms that might produce big tornadoes and hail, supercell thunderstorms, per se. There are other kind of thunderstorms too, like squall lines and whatever, but we've gotten to the point where we can distinguish among the various storm types. And we pretty much understand what makes these various thunderstorms different. When it comes to tornadoes, that's sort of another step, and that's still in the research realm. We know, for instance, that the biggest tornadoes occur in supercell thunderstorms, rotating. The whole storm is rotating. But only about 20% of all supercell thunderstorms go on to develop a tornado. So what differentiates the supercell thunderstorm that does from the one that doesn't? That's the real challenge.
I see.
And on any given day, even forecasters and researchers will be very sure there'll be supercells, but not very sure which ones will produce the tornadoes. And that you have to just simply monitor the radar and watch the storms and get storm chaser reports and whatever to help warn the public.
I see. Morris, you've talked about these big tornadoes that could spin up.
Right.
How can you sort of characterize how powerful these storms are? Not the supercells, but the tornadoes. What kind of
let's look at
winds?
in animation. This is a really up-to-date animation, 5-meter resolution, incredible amount of computer power to make this. And one of our researchers here at NCAR, George Bryan, is the researcher who was able to produce this. This is an example of a tornado, and this is just what occurs at the base of a supercell thunderstorm. So the supercell thunderstorm is on top of all of this. But within it, if we just animate it, you can see that we already beginning to get the structure of a big tornado in simulations. The key is to get this and the tornado and the thunderstorm together in a simulation, and we're still not at the point of being able to do that on a regular basis, even with our current computer capacity. Go ahead.
Well, I was just wondering, do we need more computer capacity to do it, or is there something that we just don't know about thunderstorms and tornadoes?
It's largely more computer capacity. But it's really amazing what we can do today. If we go back to the animation of the tornado, there are certain features that are critical that we know are to the tornado. For instance, you can see the winds flowing almost radially into the base of the tornado along the ground. What we've learned is from observations and from laboratory simulations and computer simulations, that's really a critical component of the tornado. The fact that you draw air in from the boundary layer at very shallow depths, sometimes only a meter or two, maybe 10 meters of air is flowing into the base and then erupting up into the tornado. The other thing we've learned is how we develop these what we call multiple vortices, which are very, very important in these very big tornadoes. The purple in this animation depicts multiple vortices in this simulation. And so we can simulate these features that we see in real life, and we can understand how they develop as a function of something we call the swirl ratio, which is a ratio of the updraft in the storm, the air that's going up, say at the top of this animation, and the amount of rotation that's available to the tornado underneath. And depending on that ratio, that swirl ratio, you can get anything from a very narrow tornado to one of these super, potentially F5 tornadoes, just based on the ratio of those two parameters. And so we're learning about that, but putting that together with the thunderstorm into a forecast model is still something that is almost out of reach still.
Maybe a few years down the road, or is that optimistic?
A few years down the road is quite reasonable.
Okay.
The researchers down in Norman, Oklahoma at the Severe Storm Center there are working on actually assimilating radar data into numerical simulations like this while storms are going on, to actually see if they can predict whether that storm is going to produce a tornado ahead of time. The problem is it takes several hours to do a simulation like that to get a prediction that's only 20 or 30 minutes long. So technically we can do it, but we can't do it quick enough yet to make it worthwhile. So it's only in the research mode that we're able to accomplish that.
So in terms of people in an area that gets a lot of tornadoes, Oklahoma or parts of the Midwest or Southeast or other regions, can you talk a little bit about what the current forecasts look like and hopefully how they might be better or more detailed in the future with this research?
Well, what we have for the forecast capability now, again, is very good forecasts of the environments, let's say, for a supercell storm outbreak. We're very, very good right now at predicting that out to several days. And this is for a general region of the country. So we can say maybe 2 or 3, sometimes 4 days out in advance, that Tornado Alley, Oklahoma, Kansas, Texas is going to be prone for a supercell outbreak. Within that region, though, we still can't pinpoint necessarily where each individual storm's going to be. There's sometimes maybe a couple of hours before the storm occurs. Then, once the storms develop, it's still somewhat of a crapshoot as to which one of those storms is going to develop a tornado. And so right now, we're still at the stage of, yes, we can predict the chances of supercell storms. We know that a good percentage of the supercell storms might produce tornadoes, but we don't know which storm is yet to produce that tornado on a given day. We almost, you don't know until maybe 15, 20 minutes before. And radar helps with that, and a lot of experience from the forecasters help to give that lead time to people so that they can act appropriately.
And 15 to 20 minutes before must be better than where we were many years ago, right? You started in the 70s, I think you said.
Yes, and I think the lead time then was in the order of 5 to 10 minutes.
Okay.
And so we're up to, for the tornado, 15 to 20 minutes, perhaps when we're having a good day. And there are occasions now where you can get a warning out to 30 minutes, 45 minutes. And the goal, I think, is to really, and this is what we think the science will eventually be able to produce, is to warn for tornadoes perhaps out to an hour, so that there is time for people to take appropriate action. Yet that will really make a difference.
Wow. And could that be as kind of finely detailed as within a county, or would it be more part of a state?
That would be part of a county.
Okay.
And we're talking 10, 20 years down the road now. But, or perhaps in 10 or 20 years, perhaps we can, an hour ahead, pinpoint the north side of Oklahoma City versus the south side of Oklahoma City. That's our hope.
Okay.
Okay. At 2 hours or 3 hours, we can maybe definitively predict there will be a supercell storm in the area of North Oklahoma City or south. And then still maybe out to 5 or 6 days, we can predict that there's a good chance of a supercell outbreak over the Oklahoma region.
Is there a key thing that we need to do? You had mentioned more powerful supercomputing. I'm guessing maybe better understanding of these storms as well, maybe better computer models?
Really, I'd say right now, the biggest gap isn't with the computer models. We have a gap perhaps in our ability to run the computer models in real time. That will be solved. Mm-hmm. You know, the usual advancement in computer capacity will eventually take care of that. I think the biggest gap in making progress right now is with the observations. Having enough observations that can be fit into the computer models. Assimilated is the technical term. We assimilate the radar data, we assimilate soundings of temperature, winds, and moisture in the area of the expected storms. And we're still struggling with getting enough observations to say for certain how a given storm is going to evolve. Our understanding has come from much more simple computer simulations, idealized simulations, where we just put one environment in. In reality, the environment over an area like Oklahoma varies considerably from the west part of the state to the east. And every given storm is moving across many different environments, often during its lifetime. That degree of information needs to be in those computer models to have any hope of replicating what nature's really doing.
That sounds great. I think we're pretty much out of time here, but I learned a lot today. Thank you. And it's exciting to learn where the science is going on this. It sounds like we have much better understanding of tornadoes and improved forecasts to look forward to. So again, thank you everybody for joining us. I'm with Dr. Morris Weisman, Senior Scientist at NCAR. I'm David Huzansky, and we'll be doing more of these Facebook Live interviews, so stay tuned. Thank you.